This lesson is for our Tuesday and Wednesday, which I think was November 1st and 2nd. We actually went into the computer lab to practice, but I did a real quick lesson starting this writing proofs topic in class first before we went to the lab. And I will tell you, just like I told them, if you're watching this for the first time, this is probably the most complex, challenging thing we do all year in geometry. It's almost like having to recall everything you've ever learned in geometry and then prove things that you didn't even know were true yet. Some of this stuff we haven't even learned yet, and you're proving that it's true. I guess they're thinking if you can prove that it's true before you learn it, it'll be easy to learn. I guess that's the concept. So it's going to be challenging. It's going to be difficult. Just hang in there. A lot of it's really just logic. So if you're good with logic, if you're a logical person and you can kind of go like that whole inductive deductive thing we just did, if you can if you followed that and you understand how to make conclusions one step at a time, then you might be okay on this. The good news is when you do this, you're typically, I think always going to be choosing from drop downs. So it's not like you have to completely come up with it from memory. And I think there's only two, or maybe it was three statements you will ever have to come up, statements or reasons that you will ever have to come up with. You're never going to have to write a complete proof all the way out. So when you see some of these really long proofs, just remember you're never going to have to create the entire thing. You're only going to have to create, basically fill in the blanks on pieces of it. So these were just a bunch of postulates. A postulate is just a true statement. It has been proven. There's no conflicting it. So again, if it says a plane contains at least three non-collinear points, then it contains three non-collinear points. There's no questioning it. That's what a postulate is. That's what a theorem is. Kind of the same thing for a definition. Like all of these concepts, there's no questioning them. They're true. Kind of like we said for a given statement. A given statement, you take that as true. You don't question it. These would all be something that could be considered given statements or reasons you could use to prove something else is true. Really nothing to do on those first. You use those in the practice, by the way. I'll show you how you use them later. How am I going to do that though? I don't think I can, see if I can shrink this down. Oh, I cannot. Shoot. All right, I'll try to figure out how to use that later. 153 is the slide. So that's just the last postulate. If two planes intersect, they form a line. There's no exception to that. If you have two planes intersecting, doesn't matter what angle they intersect at, their intersection, where they touch, basically will always be a line. So we started doing these. So here a question. The intersection of three planes is a line. Well, I can't really show you visually, but it's asking is that sometimes, always, or never true. Well, you'd have to imagine three planes coming together. So on the last page, you can see two planes coming together is definitely a line. That's a given theorem, given postulate, actually. If I took one more plane though, and I would be able to put a plane in that touched all of these points right here. If I can touch all of those points and then my plane, it basically would just be, it would just be wrapping around, if you know kind of what an accordion sort of looks like, or an index card file, it would just be another plane that just gets wedged in between this plane, this blue plane, and this orange plane right here. I just wedge a plane in right there. Well, then that plane would touch this line at every single point. So again, three planes would form a line also. But if I took that plane, that folder, or whatever you want to imagine, index card, if I tilted it so that it's not at the exact same angle as these two planes, maybe I even made it perpendicular to these planes, so like turning my plane sideways, then, oh, that's kind of cool. Then it would only touch in one point on this line. It wouldn't touch the entire line. It would just touch wherever I kind of was trying to stick that plane through. So since it sometimes makes a line and it sometimes can only be one individual point, the answer here would be sometimes. We said, well, sometimes when that happens, it's going to be a line, but not necessarily always. So that was the answer for that. Line R contains only 1 point. Well, if we go back to our postulates, it says through any 2 points, there is exactly 1 line. That's kind of the same thing, saying that a line has to have 2 points. It's a little different. It's a little bit backwards because they're talking about the line first and trying to say that a line has only 1 point. A line has to have at least 2 points. That's what this postulate's basically saying. If you only had 1 point, then you would just call it a point. It is not a line. So since we have to have 2 points, coming back to our answer, if line R exists and it's telling us it exists, it can't have just 1 point. So, oh, actually, that was in 3.3. Let's go back and look at 3.3. So that is never true. A line has to have at least 2 points. Guess let's type that in. So let's go back to 3.3. I didn't even see it had the number of the postulate. 3.3 must say, yeah. Oh, I'm sorry, it did. So this one does say a line contains at least 2 points. So we didn't even have to think about the opposite of this being true. It actually has a postulate that says, as long as you understand what the postulates should be, as long as you understand what concepts are true, I'm never going to ask you to recall like a specific number postulate. I don't even know if they have numbers. That might have just been for this particular lesson. As long as you understand that a line has to have at least 2 points. Now, this one is always true because we read that very first postulate said, through any 2 points, there is exactly 1 line. Well, that's what this is saying. Through any 2 points, there is only 1 line. There is no way to draw another line through 2 points. So that would be an always situation. And then you do have to refer back to those postulates on page 153. So if you can use your book pages, one of them is on the back of 153, so 154. But you'll see when we get to the practice problems, they ask you to do that. So 2-column proofs. So a 2-column proof is basically you're proving something is true using deductive reasoning. You're just going one step at a time and saying, okay, well, if I know this is true, then I know this is true. Okay, well, if I know this next thing is true, then I can say this next thing is true. And you're just working your way down from a given piece of information using statements that you know are true, like postulates and theorems and definitions. And eventually you're trying to prove a conclusion. You'll see in a second. One quick note. You think that this would be the magical like recipe to doing a proof. It's really not. But what it does tell you that's helpful is step 1 is always going to be given information. So you'd write a statement down that is given, and then the reason would just be given. You'll see this in a second. The last statement that you make is what you're trying to prove. Like you're always going to end with what you're trying to prove. The reason you have to come up with, so the reasoning you still have to figure out, but at least you know the last statement is whatever you're trying to prove. So those are some maybe freebie answers on quizzes or even on the district. The first reason is always going to just be given. The first statement is always going to be some kind of given statement. And then the last statement is always going to be what you're trying to prove. Unfortunately, this step 2 and step 3 really don't do you no good. You still have to come up with everything in between. This is just telling you you do it using deductive reasoning and that you can use theorems, postulates, definitions, anything you know is true in math. But you still got to figure out what they are. So then let's do a couple of quick proofs. So for this particular proof, so this is a pretty common concept you'll see in proofs about a midpoint. There's really only, I want you to think about, if I know this point Q is a midpoint, what is it that I can say immediately about this figure, about this line segment that I've just now divided into 2 line segments? I want you to think about that and say what you can say is true. So you can pause it. Hopefully you came up with this statement. Hopefully now that you've unpaused. There's only one thing somebody telling me that Q is a midpoint would be like helpful for. There's only one reason that information is helpful. And that's to tell me that this line segment PQ is the same length as this line segment QR. That's it. You could argue that, well, I mean, I guess you could argue that, well, it tells us also that if Q is between P and R, PQ plus QR equals PR. That is true, but telling us, they don't have to tell us it's a midpoint to tell us that. They just have to tell us Q is between PR. Telling us specifically that it's a midpoint, they're trying to get you to say this segment is the same length as this segment, or that they're congruent, which is actually sort of two different things. So as soon as we have, oh, again, first statement is the given information. So here's the difference between a statement and a reason. The statement is what they give you, basically. What you're saying is true. The reason it's true in this case is given. So a reason is why it's true. The statement is what is true. So our next thing, oh, I can't write in here. Back and type. The next thing we could say is, well, I know that P, Q, oh man, I can't. Oh, here we go. All right. So I know that, and I'm not going to do it the way they do it, just to make it PQ, or maybe this is the way they do it. Actually, it is the way they do it. PQ, I don't have the little line segment thing over, whatever, that's wrong, is equal to QR. That's what I can say. There we go. So I know that if this is the midpoint, that the length of this equals the length of that, whatever the length is. So that's what I've just typed in. The reason for that is the definition of midpoint. So that's the reason. The length equaling the length is the definition of a midpoint. Now here's the weird thing, and again, I would not have even written this proof like this, frankly. I guess they're trying to prove it though, so you don't really have any other way to write it. This is now saying, therefore, PQ is congruent to QR, which is what we're trying to prove. Remember, the last statement is always what you're trying to prove. Well, this is the midpoint theorem, which again is kind of the same, saying the same thing. I had to even look up why they were different. So the midpoint theorem talks about congruence. So if you want to say two things are congruent, that means the shape is the same. So this line segment, if I wanted to, I could lay it exactly on top of this, and they would match up perfectly. That's what congruence means. PQ equaling QR, or the definition of a midpoint, means that the length is equal to the length here. So if we had numbers, we could use those numbers to solve for a variable or something like that. That's the only difference between them. They use both of these two things in a couple of proofs that I saw. My proofs will not be that bad, although you may wind up taking it on the computer. So I guess maybe they will include both theorems in some of them. Just remember there's a very small difference as long as you understand that one segment has to equal the other segment. We are not doing anything with flow proofs. So here's another proof. So it says given B is the midpoint of AC. So right here, again, if they're telling you something about a midpoint, you should already know what statement you're going to be making based on B being the midpoint of AC. It also tells us C is the midpoint of DE. Again, you should already know a statement you're going to be making. So now what we're going to do is prove that BC, so here's BC, equals DC. Here's DC. Oh, and then they also give us another statement that says AB, so this segment here equals CE, this segment here. So I know it's a bunch of stuff going on, but we're just going to take it one step at a time. So if I know, oh, and again, they write the statement that's given, B is the midpoint of AC, C is the midpoint of DE, and it is given. They did not write this given statement. I might have written it, but I guess they're saving it for when they need it later. From B is the midpoint of AC, I know, just like we said before, AB has to equal BC. I think I have to correct this. So AB has to equal C, right? So that's the first thing I can say based on this B is the midpoint statement. Now, just like I said there, and just like I would say in every midpoint problem, I could say, okay, well, if I know C is the midpoint of DE, I can make a statement that DC equals CE. So I could say then DC equals CE, and C is the midpoint. So you see, they already wrote down the reason for that one, definition of a midpoint. That a lot of times, if you read either the statement that they give you or the reason that they give you, that'll kind of tell you what you need to fill out on the other side. Every once in a while, though, like this line 4, they don't give you either of those. So that's when it's a little trickier to come up with. But if they give you one side and just not the other side, that might help you figure out what you need to write in the missing blanks or from the missing drop down. All right, so now here's where I would kind of do the proof differently. They break this out into 2 steps. I'll show you that I would just do it in 1 step in a second. So a hint that I gave them in class, anytime you see a bunch of equal signs, like there's an equal sign here, an equal sign here, an equal sign here, equal signs down here, substitution is going to probably come into play. There are some other math properties you could use, but you'd be safe to always use substitution because those other math properties are based on substitution anyway. So your proof would be shorter if you use them. If you want to look them up, one of them is called the transitive property. You can look that up, but it's a quicker version of substitution, basically. So now, again, if I see a bunch of equal signs, I'm thinking and I want to somehow get from here down to here, I'm just going to start replacing things. So if I know that AB equals BC, I could substitute for AB. I could say, okay, well, wait a minute. If I'm trying to get BC in my final statement, I could bring BC in right now because I know AB is the same thing as BC. So I'm just going to substitute in and I'm going to say BC equals, and I guess I'll do it like yeah, I'll do it like they did it first. So BC equals CE. I accept. So all I did again, I just said, okay, well, I know these 2 things are the same, so I can change AB out for BC. Substituted that in. Well, then, just like I did there, I can say, okay, well, wait a minute. If I'm trying to get to DC, I know DC is the same exact thing as CE. So I could replace this CE down here with DC. They're the same thing, so I can take one out, put the other one in. Oh, my reason again was substitution. So now I've substituted in, they've already got the reason there, so that kind of tells me what I needed to do was to substitute for this, and there's my proof. I would not have done this last line down here when I did a proof. I would have substituted in both things right here. I would have substituted in BC for AB and DC for CE all in the same line, so I would have already been here. If you did that, that would have been fine if you understand that you can just substitute them in both at the same time. I'm not sure why they did it separately, but we didn't really do anything with flow proofs. There are some in the practice, so just try to follow through. I gave them some worksheets in class that were already solved proofs, like they were already worked out. There was nothing they had to do. It'd be a good idea to get those before the quiz. The more you just read through proofs and you see how the reasoning flows, even if you can't necessarily recall all of this stuff on your own, the more you read through them, like now that we're done, if you can just read through and follow, okay, do I understand why this is here? Well, yeah, it was given. Do I understand what they did here? Well, yeah, I know that if they give me a midpoint, that means the 2 small segments are equal. Do I understand how they got this? Well, yeah, they just gave that to me. Do I understand how they went from here to here? Well, yeah, if I know all of these things are equal, then I can just exchange for AB. I can just replace that with BC. I can replace CE with DC. So if you just look through some proofs that are already solved, there are tons of them. Like just look up geometry proofs or solved proofs if you want to just read through some. If it looks super complex, don't worry too much about it. The ones I gave in class were not super complex. Anything with midpoints and substitutions and additive properties of segments, those kind of things. And then we'll get to additive properties of angles. Basically, if they're using the reasons that we've already learned in geometry, then those are probably pretty decent proofs. I think that was all we did. Then we went into the then we went into the lab, and this is what the practice was. You just went through all the practice problems. I said, make sure you get through 14. So you need to make sure you get through 14. If you don't understand how to do something, just, I think when you do, so the assignment is still in there. You can still go in and do the assignment. So it should show up on your dashboard, your first page, for at least another week. Today's the 6th. So it should be in there, I think, until next Friday. After that, you can still submit it, but I think you may have to find it after that because it probably will be removed from your page. But this was the really good proof here, number 11, and I think 13 was what I said, a really good proof to practice. Yeah, 13 is also a good proof to practice. And it has tools in there when you do the assignment. It has tools with drop downs. Like right now, you'd have to come up with all of this stuff on your own. So make sure you go in and you do the assignment online, in the online book. Hill. Here, I'll show you how to get to that real quick. Close this now. So there, you see right there, it's writing proofs. So you'll see if we go into writing proofs, I can just view it maybe. This will let me use it. Oh, that's just viewing your, can I? Oh, too, I'm gonna, since we're probably not doing the quiz for a little while, I'm just gonna do this all the way through the end. Now that gives people even more. You may not have this quiz for a little while. Okay. All right, so let me show you how you get to your McGraw-Hill book. So you go into your Clever, it looks like this. I have it saved as a favorite, so that's why it's up top. You may have to scroll down, or you can type into the search McGraw-Hill. Once you go into McGraw-Hill, you have to click on the icon that looks like our book that we use in class, that Florida Reveal book where you tear the pages out. So you have this book right here. It said not algebra. Yours is the geometry version. So click on that. Once you click on that, it should be right there on your first page. If you want to do more, oh, actually, I'm sorry. This is the one that you should be doing. I guess this one is popping up first, so let me change that one. I want to make sure that one is. Oh, I meant to change date. Shoot. All right, I can do it. So again, do the one that says practice first. That matches up with the book pages. And then do the one that says, that should make it the second one. If I then do the one that says extra practice if you really want to do extra practice. And that's everything for this particular lesson on proofs. We have several more lessons on proofs though, probably before.